Yeah, okay, welcome back. And as I promised for part B, we are going to look at the electromagnetic spectrum to begin. There is a diagram of this that goes into a little more detail in the book, and so you should definitely have a look at that. But on this one, I also wrote in the relationship between energy and wavelength and frequency, or frequency and wavelength. And I think it personally, to me, makes more sense to arrange the electromagnetic spectrum from low energy to high energy, whereas the book, for some reason, has done it the other way around. And so you can look at this, way of doing it. You can look at the way the book does it, and whichever way makes sense will be fine. Then sort of concentrate on that one. Anyway, going from low energy to high energy, you're going from, again, low frequency to high frequency, or long wavelength to short wavelength. So notice that energy varies the same way as frequency, and it varies the opposite way from wavelength. So the lowest energy, or the lowest frequency, or the longest wavelength type of electromagnetic radiation would be radio or TV waves. At the bottom, they have wavelengths that are on the order of a kilometer, or like half a mile or more sometimes. And so that's going to be a very, very long wavelength and very low energy. As I mentioned before, this energy is so low that we're being bombarded with radio and TV signals all the time, pretty much 24/7 for our entire lives, unless you're out in the middle of the Sahara Desert or something. And we don't even know it, because the energy is so low that it has no effect on us. If you have a radio with a crystal that's tuned the right way, you can then this electromagnetic radiation will make the crystal vibrate, and then you can amplify that vibration and listen to the radio as sound. But that level of energy has no effect on us. The next type of electromagnetic radiation would be microwaves, or radar type energy. This has wavelengths on the order of, say, from about 10 meters to 0.0001 meters, or 10 to the minus 4 meters. And it's still pretty low energy. We are being bombarded by microwaves all the time, and radar, because of things like, well, radar, whether police radar or radar from airports, and microwaves for various forms of communications, like some cell phones use electromagnetic radiation that's into the microwave range. Again, we're being bombarded by that stuff all the time, and we don't even know it because it's so low in energy. Now, your microwave oven, on the other hand, produces a lot of power, which means basically it produces a very intense, high amplitude of microwave radiation. So if you were to get too close to that and if the oven didn't have shielding on it, that could be a problem. But normally, microwaves, radar, no problem. Similar with infrared. Infrared has wavelengths ranging from about 10 to the minus 4 meters to about 10 to the minus, say, 6, around there. And infrared is felt by us mostly as heat, and it's a very low energy radiation. Again, we don't have to limit our exposure to it. And it's called infrared because in Latin, the word infra means below. And so this is called infrared because it's the type of electromagnetic radiation that comes right below, in terms of energy, red light. Because the next stop on the electromagnetic spectrum is visible light. And I've squeezed visible light into this narrow little band here, because if you look at the electromagnetic spectrum laid out sort of linearly by wavelength, you'll notice that visible light really does take up a very small slice of the electromagnetic spectrum, which is kind of amazing because so much of how we interact with the world around us is based on visible light. it's kind of ironic that visible light is actually such a small part of the electromagnetic spectrum, but it is. And within that visible slice of the electromagnetic spectrum, we have going from lowest energy to highest, red, orange, yellow, green, blue, indigo, and violet light. So the visible range starts at a wavelength of about we'll call that 700 nanometers in terms of wavelength. And that would be about 7 times 10 to the minus 7 meters. And then violet light ends at a wavelength of about 300, we'll call it 400. Actually, it's probably a better number than 350. 400 nanometers, or 4.0 times 10 to the minus 7 meters. And it's just within that narrow band. That's the only kind of electromagnetic radiation that we can actually see. All of this other stuff is completely invisible. Although we're starting to get to the point where we can start to notice that the electromagnetic radiation is there, even if we can't see it. Because if you go above violet in terms of energy, you've hit ultraviolet. Ultraviolet is called that because in Latin, ultra means above or beyond. And so ultraviolet literally means beyond violet in terms of energy. And this is the next highest energy above violet light. Ultraviolet energy has enough energy that we're now starting to get into what's called ionizing energy. From ultraviolet on up is what is known as ionizing energy. And what we mean by that is this is energy that has types of electromagnetic radiation that have enough energy to cause ionization of biological molecules, like, say, proteins or enzymes in your body. And ion, as we've seen just with simple atoms or molecules, like, say, turning chlorine into chloride or turning oxygen into oxide, ionizing a substance can change its properties quite significantly. And that is actually a bad thing when those substances that are being ionized are in your body and things that your body depends on to keep it running and keep you alive. So if a protein, the functions of proteins, proteins in your body and enzymes are very large, complicated molecules, and they're long chains, and they fold around in a certain way. And that shape of that molecule is responsible for its function. And if you change the shape, you change its function. Well, ionizing a protein or an enzyme is a good way to change its shape, because now you have maybe a positive charge in one part of the molecule and a negative charge in another part of the molecule. They're going to be attracted to each other, and they're going to come together, even if it means folding the molecule in a different way. And folding in a different way means that it's not going to work. It's not going to do what it's supposed to do, and it might start doing stuff that it's not supposed to do, which can be a very bad thing. And the likelihood of that happening increases as the energy of the electromagnetic radiation increases. So there's a certain chance of that happening with ultraviolet radiation, which can lead to ionization of molecules, which can result in cancer. And the chances of that happening are even greater with the higher energy forms of electromagnetic radiation. So with ultraviolet, this is what causes sunburns. And of course, excessive exposure to ultraviolet radiation can cause skin cancer. By the time you get up to X-rays, you're at a high enough energy that X-rays are actually able to penetrate right through your body. And they have enough energy that they can actually cause cancer not only on the skin, but within your body as well, if you have excessive exposure. And that's why when you do go to get X-rays, the technician puts a lead apron on you so that you don't irradiate parts of your body that you don't want X-rayed. And then they duck behind a lead screen before they actually turn the machine on, because they're using that machine every day and they really want to minimize their exposure. And then by the time we get up to gamma rays and cosmic rays, this is basically what we think of as nuclear radiation. So nuclear reactors and nuclear bombs give off gamma rays. Gamma rays also come from, well, the sun. Actually, all of these forms of electromagnetic radiation come from stars, like our sun. And they can also come from other sources out in the universe, like quasars and pulsars and things like that. Fortunately for us, Earth's magnetic field and its atmosphere is capable of limiting the amount of ionizing radiation that makes it through to Earth. We basically have some ultraviolet, enough, more than we need, really, and we do have to limit our exposure to the sun. But in terms of X-rays and gamma rays, we basically get nothing coming through to the surface of the Earth, which is a good thing, because especially with gamma rays, basically once is enough. You get hit by gamma rays once, you're dead. So it's really a good thing that we don't have to encounter them very often. That can be a problem, though, with things like space travel, because once you're outside Earth's atmosphere and outside Earth's magnetic field, you have very little protection against things like that. If you're in a space capsule or a space suit, obviously you can't line it with lead, because it's something, I think, like $1 million a pound for getting something into space. So you line your capsule with lead, yeah, you'll be safe from X-rays and gamma rays, but it'll cost like $10 trillion to get the thing off the ground. So there's sort of a compromise there. You basically, if you're going beyond the Earth's atmosphere, you're taking your chances with things like X-rays and gamma rays. Fortunately, so far, it has, the gamble is paid off, but it may not always. So an example of sort of calculations involving things like wavelength and speed of light and frequency would be, say, some cell phone signals have a frequency of 850 megahertz. And so what would be, say what? Why did I put an E on the end of that? What is the wavelength in meters? Remembering that speed of light, or c, is 3 times 10 to the 8th meters per second. So the equation we saw a couple of minutes ago showed us lambda, that is wavelength, is equal to speed of light divided by frequency. So that's 3 times 10 to the 8th meters per second divided by, now we were given the frequency as 850 megahertz, which you can write. You don't have to actually stick with proper scientific notation in changing this to hertz, because this is not the final answer for the question. So you don't have to use proper scientific notation in intermediate answers. So if you have 850 megahertz, that just means 850 million hertz, because mega means a million, or 10 to the 6th. So 850 megahertz would be 850 times 10 to the 6th hertz, or 850 times 10 to the 6th inverse seconds. And that's the easy way to do it. You could convert this to proper scientific notation. It would be 8.50 times 10 to the 8th hertz. But that requires, the more steps you take, the more likely you are to make a mistake. And so I think it's easiest just to leave it as 850 times 10 to the 6th, because like I said, that's not your final answer anyway. So that's going to be 3 times 10 to the 8th meters per second divided by 850 times 10 to the 6th seconds to the minus 1. And this is equivalent to speed of light divided, or times 1 over the wavelength. Sorry, 1 over the frequency. So speed of light times 1 over the frequency. That's what we've got here. You can do it either way. Speed of light would be 3 times 10 to the 8th meters over 1 second. And 1 over the frequency would be 1 second over 1 second for every 850 times 10 to the sixth. And then I wrote in waves in parentheses because that's what we're talking about, even though we don't normally write down the word waves. And then you'll notice here how the units cancel. Got seconds on the bottom, seconds on the top, they cancel out. Meters ends up being the only unit left. And that's good because we want a length unit. And in fact, we want it in meters. So working all of this out, we get 0.353 meters. And that is the wavelength. And that would fall about 3.53 times 10 to the minus 1 meters would fall just inside the microwave range. Oops, just inside, because the microwave range basically starts at about 10 meters and goes to 10 to the minus 4 meters approximately. So 10 to the minus 1 would be sort of towards this end, the low energy end of the microwave range. All right. The next topic for us to deal with is the idea of interference patterns. Interference patterns are important to the history of the development of the structure of the atom because, well, they're basically important in developing the wave-particle duality theory of light. And that is, they demonstrate the idea of interference between waves. When waves are in the same place at the same time, they can interfere in ways that they enhance each other, or they can interfere in ways that they counteract each other. And kind of the point here is that that can only happen if you're talking about waves. This kind of thing would not happen if light were made up entirely of regular everyday particles. Okay, so interference patterns are what occur when two or more waves come together in the same space at the same time. And specifically what they did here is what's shown in figure 6.6. They basically took a piece of metal with two very thin slits that were cut into the metal very close to each other, about one wavelength of light apart from each other, in fact. So that is really, really close. And the interference pattern you see when a single source of light shines light through those two slits is interesting because you end up with a bunch of bands, dark bands and light bands. And the dark bands are known as destructive interference. They're caused by instances in which the waves meet perfectly out of sync. That is, now these waves of light going through the two slits, they're coming from the same light source. So they have the same wavelength. And if they're perfectly out of sync with each other, then in a given spot, then basically you've got the peak of one wave and the trough of the other wave coinciding with each other. So the black wave would be the wave of light coming through one slit, and the red line would be the wave of light coming through the other slit. And you notice how for any given position, you might have the peak of one wave and the trough of the other, or the trough of one wave and the peak of the other, and so on. And they end up canceling out. And that's why you have dark bands in the spectrum, because of this destructive interference. The bright areas, or the brightest areas, are constructive interference. That is where the two waves, and remember, these waves are the same wavelength because they're from the same light source, when they meet in sync, so that the peak of one wave and the peak of the other wave coincide, and the troughs coincide, and so on. What happens when that happens is they augment each other. So the light ends up even brighter than it was originally, or looking even brighter than it was originally. And those are the brightest areas of the interference pattern. And then you have areas around the edges where it's maybe, there's light, but it's not the maximum light, but it's not totally dark either. And those would be areas where the waves meet in ways that are not perfectly in sync, but not totally out of sync either. And that's a case where they might augment each other a little bit, or they might cancel each other out a little bit, but not completely. And so those are the intermediate areas. This is kind of similar to the interference pattern you get in water waves. If you drop 2 stones into calm water very close to each other, you'll get a series of interfering waves. And you'll get some spots where there's basically no wave at all. That's destructive interference. And you'll get other spots where there's a fairly big wave, and that's constructive interference. Anyway, the existence of interference patterns, the main importance of that is that they confirm that light travels as waves. If light traveled as conventional particles, then that wouldn't happen. You wouldn't get that. Okay, the next section is actually on standing waves. That gets really physicsy really fast, and we can discuss that when we come to it, when we start getting into the actual structure of the atom. So I'm going to put that off until later, and we skip over that section, and we come to the section on blackbody radiation. Blackbody radiation is the type of radiation that an object gives off because it's hot. And that radiation tends to take the form of a continuous spectrum. That is essentially a rainbow of colors where one color bleeds into the next with no gaps between them, which is what you see in a normal rainbow, because the sun is a black body. It's kind of a strange thing to call it because the sun is anything but black, but the sun is definitely emitting electromagnetic radiation because it's hot. And so it emits all of the colors in the rainbow continuously, every shade of every color with no gaps between them. And that is an idea, that is the idea of blackbody radiation, that seems very natural to us because it matches the light from the sun. You have certain other light sources like fluorescent lights that will give off sort of representative colors across the visible spectrum. And our brain sees those colors and averages those colors out to white, but it's a very unnatural white. So it's white, but it's not a natural white like you'd expect from the sun. Our brains, when it sees all of the shades of all of the colors like it does from the sun, also averages those colors out to white, but it's kind of a different shade of white than you get from something like a fluorescent bulb. And so that's why fluorescent bulbs often seem really artificial and irritating, while incandescent bulbs, the old Edison style light bulbs with a metal filament in them, they give off light because they're hot. And so regular incandescent bulbs are black bodies, and they give off light in a spectrum that's very similar to that of the sun. And so that light seems very natural to us, whereas fluorescent lights and LEDs too, for that matter, often don't. The actual temperature of the black body will control the relative brightnesses or the relative intensities or amplitudes of light at various wavelengths or frequencies, depending on how you want to look at it. And as it turns out, the blackbody radiation with a temperature of 5,250 degrees Celsius gives off a spectrum of light that's almost identical to that of the sun. So if you're looking for, if you have light bulbs that list a certain temperature on them, that's the temperature you're looking for if you want something that mimics sunlight. Although the temperatures on the bulb packages are often in terms of Kelvin. So let's see, in terms of Kelvin, 5250 plus 273 would be 5523. So that would be equivalent to natural sunlight. Okay, so the maximum, like I said, the maximum intensity of the light shifts to shorter wavelengths as the temperature increases. And when it gets to 5250 Celsius or 5523 Kelvin, that's where it actually has a spectrum that's almost identical to sunlight. Hot objects, when they're only a little bit hot, start out looking red, sort of a dark red. And as they get hotter and hotter and hotter, the wavelengths shifts to shorter wavelengths, or the intensity shifts to shorter wavelengths, and you progress through orange and then yellow and finally white. By the time something gets white hot, it's so hot that the maximum in intensities within the visible range is right about in the middle of the visible range. So again, our brains average all of those colors out and comes up with white. Now, the problem is this wouldn't make sense if light were a particle, because the classical theory says that objects at room temperature should be and it's kind of a complicated theory, but just suffice to say, according to Newtonian physics anyway, any object at room temperature should be emitting basically infinite ultraviolet radiation. And of course, that's obviously not true. If it were, we'd all be dead from skin cancer by the age of about 2. And so that is known as the ultraviolet catastrophe, because classic Newtonian physics leads to expectations like the emission from emission of ultraviolet radiation from things at room temperature that just don't happen. And so it was obvious for a fairly long time that there was more to the situation than classical physics was able to convey. Along about 1900, a guy named Max Planck came along and resolved the ultraviolet catastrophe because he concluded that atoms vibrating at increasing frequencies as the temperature increases leads to emission of electromagnetic radiation. But atoms can only have certain values for energy. So the energies available to these atoms are not continuous like a rainbow is, but actually have certain values that are allowed and certain other values that are not allowed. And in other words, energy is quantized. What that really means is quantized means that it's divided up into certain specific values, and those values are very small and very close together. Planck came up with the equation energy, that is the energy of the energy of electromagnetic radiation is equal to some number n times h nu. Now, nu, of course, is the frequency of the electromagnetic radiation. H is sort of a proportionality constant that Planck himself came up with, and so it's known to this day as Planck's constant, and it has a value of 6.626 times 10 to the minus 34 joule seconds. Those are the units. And n is a positive integer. So it could be 1, 2, 3, 4, and so on. In other words, this is how the energy is quantized, because n can only have certain numbers and certain other numbers are not allowed. So 1.5, not allowed. 1.97, not allowed. 2, allowed, and so on. These quantized values of energy end up being very close to each other. The differences, whether you multiply it by 1 or 2 or 3 or 4, ends up being a very tiny difference. And that's why for many, many years, the energy seemed to be continuous, like a rainbow, when in fact, it's actually a bunch of fine little lines right next to each other, very close to each other. And the analogy that I can think of is to say a computer-drawn curve. If you look at a curve drawn by a computer, particularly on a printer, it'll look like a smooth curve from a distance. But if you look at it close up, you'll see that it's actually a series of horizontal and vertical lines in succession, like a little stair step. And because that's all the computer is capable of drawing, it's not really capable of drawing a continuous smooth curve. And the resolution of the computer will depend how far away you have to get for the curve to look like a smooth curve versus a stair step. But this is sort of like the idea. If you're looking like the idea that Planck exposed, basically, if you're looking at it from a certain distance, then it might look like the values are continuous. Whereas if you look closely enough, they're actually quantized into like individual steps. So that was a big leap forward in terms of physics and ultimately chemistry also. I see we've reached 30 minutes again, so I'm going to leave it there and we'll pick up the photoelectric effect in part C. So I'll be right back.